Some predictions should never be forced. I'll build a reject option classifier in scikit-learn, so low confidence cases abstain instead of causing bad decisions. This is the pattern you'll be able to implement by the end, which calibrates probabilities and defers uncertain predictions based on a coverage target. I'm Professor Pi, teaching AI foundations with simple Python. In many applied pipelines, a wrong automated decision costs more than no decision. Think medical triage, loan approvals, or safety systems. You want the model to answer when it is confident and defer to a human when it is not. That is the problem reject option classification with abstention solves. Success is higher trust and fewer catastrophic mistakes at the cost of asking for help sometimes. Intuitively, the approach is simple. Train a classifier, make its probability estimates reliable, then choose a confidence threshold. If the top probability is below that threshold, defer. Strengths are clearer operating points and predictable trade-offs. Weaknesses are you must accept deferred work and calibrate probabilities carefully. We will build a small end-to-end example that you can expand. You will train a baseline classifier, calibrate its probabilities, test a simple abstain rule that rejects low confidence cases, and tune a threshold to meet a coverage target. No deep math, just clear steps that map directly to real systems. Now we start with a baseline. Now we'll fit a baseline and measure forced accuracy. This snippet trains a scikit-learn logistic regression and reports the forced accuracy on a held-out test split. It first creates a simple binary dataset with make classification, so there is signal, but also some noise. The train test split function separates training and test data in a reproducible way with stratification to keep class balance. The logistic regression model is fit on XTR and YTR, then used to predict labels for XTE. Finally, accuracy score computes the fraction of correct decisions when the model is forced to answer every case, regardless of confidence. The printed forced accuracy is your no abstain baseline to improve upon with a reject option. Next, we will calibrate the model probabilities so they reflect real likelihoods. This example calibrates scikit-learn probabilities using CalibratedClassifierCV with a sigmoid mapping and evaluates calibration via Breyer score. The vector prob raw comes from clf.predictproba and represents uncalibrated class 1 probabilities. The Breyer score loss function measures squared error between true labels and predicted probabilities. Lower is better. The CalibratedClassifierCV object wraps the trained classifier, learns a monotonic mapping with cross-validation, and then probcal holds calibrated probabilities for the test set. Comparing Breyer before and Breyer after shows how well probabilities reflect true likelihoods. Increasing CV can stabilize the mapping, but costs time. Switching to method equals isotonic can help with more flexible, non-monotonic reliability shapes. A lower Breyer after indicates improved probability calibration that enables safer abstention. Now, we will add a simple abstain rule and measure selective performance. This code introduces a reject option by abstaining when the maximum class probability is below a threshold. The function abstain metrics takes probabilities prob, true labels y, and a threshold tau. It computes confidence as the row-wise maximum, keeps cases with confidence above tau, and reports coverage as the kept fraction. For the selected subset, it derives predictions via argmax and computes selective risk, which is the error rate among decided cases only. Setting tau higher reduces coverage, but typically lowers selective risk. Setting it lower increases coverage, but risks more mistakes. The printed coverage and selective risk show how much you decide and how reliably you do so at tau equals 0.8. Next, we will search for a threshold that meets a coverage target while minimizing errors. This snippet searches scikit-learn probabilities for a threshold that satisfies a minimum coverage, and then minimizes selective risk. It defines a grid of taus and a target coverage, then evaluates coverage and risk with abstain metrics for each candidate. Thresholds meeting the target are gathered, and the one with the smallest risk is chosen, breaking ties by preferring higher coverage. If none meet the target, it falls back to the threshold with the highest possible coverage. Increasing target cov forces more decisions and typically moves the chosen threshold downward, while lowering it permits a higher threshold and fewer safer decisions. The printed chosen tau and kept fraction confirm the selected operating point. Now we will package the calibrated model and threshold into a minimal reject option classifier and inspect deployment metrics. This example wraps the calibrated scikit-learn model in a minimal reject option classifier and reports pragmatic deployment metrics. The reject option classifier stores the calibrated estimator and a threshold, then predicts by computing predict proba and abstaining when no class exceeds the threshold. It encodes abstention as -1 and otherwise returns the predicted class index via argmax. Using the tuned threshold t-best, it generates selective predictions for the test set, then computes the decision mask, the accuracy among decided cases, and the defer rate. Raising the threshold increases defer rate, but often improves decision accuracy. The printed defer rate and decision accuracy summarize how often the system defers and how reliably it answers when it does. This toy workflow maps directly to a production gating step. Replace the toy dataset with your real features and use the same calibration and threshold search. The same metrics, coverage and selective risk, tell you when to push a case to human review. Recap. .os. It is a simple pattern. Calibrate probabilities, threshold by confidence, defer low confidence cases. Use it when mistakes are costly and human fallback is available. One caveat is that deferring shifts workload to human reviewers, and that calibration requires representative validation data. Next step, tune the coverage target and the threshold grid on a realistic validation set, so you can choose the exact trade-off between automation and safety. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.